Yes, what is root 3 divided by 3?
Zero 0.58.
0.577.
Come again, 0.
0.577.
So 0.577. So approximately 0.58. So meaning Asumene's answer earlier was right. Amma, check and then to determine where you went wrong, okay?
Okay, sir.
Okay, so that is the answer. Any question? Any question with a solution? Okay. I just forwarded a question to the platform that we have to check the question out. And let's go through the question. The question says that one end of a light inextensible string is attached to a horizontal ceiling, and a particle of 4 kilograms is attached to the other end of the string. The particle is pulled sideways by a horizontal force of 20 Newton until the equilibrium position is reached. Find the tension in the string, capital T, and the angle theta which the string makes with the vertical in equilibrium. All right. Let's quickly, can I clean the board? Can I clean the board, class? Hey, fellow professors, you are not talking.
Yes, please, you can clean the
Yes,
board.
please.
Your silence means that clean the board, so I'm giving cleaning it. Okay, so you see, side questions often would be clearer if you put it into drawing. I'm coming in. Give me some seconds to close the curtain. If you put the information into drawing, it helps the answering of the question. So one end of a light inextensible string is attached to a horizontal ceiling. So I draw a horizontal ceiling. A ceiling is always horizontal. So this is my ceiling, which is a support. So one end of a string, we cannot be extended or, okay, you cannot stretch inextensible. It's connected to, so this is a string, one end of it is connected to the ceiling. And a particle of 4 kilograms is attached to the other end of the string. So the other end of the string has a particle of mass 4 kilograms. So this is a mass 4 kg. The particle is pulled sideways by a horizontal force of 20 Newton. So we have a force, a horizontal force pulling this. And this is a horizontal force. So let that vector look like a horizontal. So 20 Newton is that horizontal force pulling the mass. So the particle is pulled sideways by a horizontal force of 20 Newton until the equilibrium position is reached. So clearly, when this is pulled, the string which holds this mass will certainly change. Initially, it is this. So if I have a horizontal force pulling this spring, okay, it will tilt at an angle to this vertical. So the string now would become something like this. Okay, and then the mass will now be here because it is being pulled by a force. So this is now the imaginary vertical line, and this is the string after it's being pulled by the horizontal force of 20 Newton. Class, are we okay?
Yes, please.
No, please continue.
Yes.
Okay, so what I'm saying is that initially, this is it. This mass is attached to a string. This is the string, this is the mass. Initially, this is it. Before the horizontal force is applied in pulling the mass. So the mass is now pulled by a horizontal force of 20 Newton. Now, if this is the situation and it is pulled, the string, because this is pulling it, the string will tilt at an angle. It will no more be vertical, but it will be inclined. And so the mass will now be here because the mass is being pulled. So after it being pulled, this is how the drawing is. This is the angle between the string and then the imaginary vertical, theta. So that's what we are going to have here, theta. This is the length of the string attached to the ceiling. It is inclined now because it is being pulled. Please, are we okay now, all of us? So the question demands that calculate. So it is pulled until equilibrium position is obtained. What is the equilibrium position? The equilibrium position is obtained when the total forces acting on the mass is equal to 0. So the horizontal force must be balanced by a certain force. Now the vertical weight of the mass must be balanced by this. So when we have the net force acting on the mass being equal to 0, then equilibrium position is obtained. Is that okay? So it is being pulled until a net force of 0 is obtained. Now, this is a string. The string supports the mass by exerting a certain force, tensional force. Okay, so the string has a tensional force in it. Now, the force is always directed to where the support is, where the string and then the mass is being supported. It is supported by the ceiling. So the tension in the string acts in the direction of where the support is. So it will go up. Meaning if the ceiling is here, I will change the direction downwards because the tension in the string always acts in the direction of the tension. The support. Okay. Now, if you look at the tension, the tensional force in the string acts at an angle to this vertical. Meaning we have to resolve this tension into components. In our physics, it said that whenever a force or a vector quantity acts at an angle, it can be resolved into two components, the vertical and then the horizontal component. So let's resolve to get, this is the horizontal component of this force, and this side becomes the vertical component of the tension T. What will be the horizontal component of the tension? Yes, please, this is similar to when we have something like this, the tension acting down, and then the angle of tilt is here. When we resolve it, this is the vertical, this is the horizontal. This is the vertical, and then this is the horizontal. So what will be this component? This horizontal component is this. And then the vertical component will be this. So what is this side? Yes. Who can quickly resolve this for me?
mg cos theta.
Come again.
mg cos theta.
Lizzie, I will not accept mg cos theta. Think through and come again. Why am I not accepting mg cos theta, class?
mg sin theta.
I will not accept mg sin theta.
Okay, t cos theta.
It must be t cos theta because we are resolving the tension into components. Okay?
Yes,
So this must
Yes.
be t cos theta. What about this component? The
t sin theta.
this is t sin theta. Good. Now, the question said that it is pulled until an equilibrium is obtained, meaning the vertical component, the weight, which is mg, must be balanced by this component. Now, equal vectors. T cos theta will be the same as T cos theta here is the same. Vectors are equal if they have the same magnitude, direction, and power. So we can bring this here. So we can deduce that T cos theta is equal to mg because equilibrium position is obtained. Then the T sin theta, which is this component, is also balanced by 20. Newton's first law, equilibrium position is obtained, right? Are we okay?
Yes, please.
We can easily calculate this since we know the mass and we have gravity. We are told that the mass is 4. So the mg, the weight is 14 Newton. Okay, now this is equation 2. I'm looking for theta. So let's divide equation 2 by equation 1. Divide equation 2 by equation 1. If we divide equation 2 by equation 1, we have t sine theta over t cos theta is equal to 20 over 40. Somebody may ask, say, why not equation 1 by equation 2? Because we are doing this because we know the ratio of sine and cosine is equal to tangent. So that's the reason why we are dividing equation 2 by equation 1. Please, is that okay?
Yes, please.
So we have sine theta over cos theta giving us tan theta is equal to half, 0.5. Let's take the tan inverse of 0.5. What's the tan inverse of 0.5?
26.57.
So theta is 26.57 degrees. That is the angle of tilt. The next question requires that we find the tension in the string. Okay, so once we have theta, we can use either equation 1 or 2 to find the tension, capital T. So go ahead and make me proud. Help me determine the tension in the string. Adwa, what did you get for the tension in a string?
Please, I had 44.74 Newton.
Okay. I think Adwa is right. So, but let's have a confirmation. So, using equation 1, T cos theta is equal to 40. We found theta to be 26.57. So T cos of 26.57 is equal to 40. Therefore, T is equal to 40 divided by cos 26.57. Charlotte, what is 40 divided by cos 26.57?
Mr. Dia, please. My calculator said error.
Okay, somebody should step in. Lizzie and Co. Asmani, Chrysler, you are there. Chrysler, you are also there. Isra, you are there.
44.7.
4.7.
44.71.
Okay, so
0.71.
all right.
Yeah.
You can also use equation 2, and the value will still be the same. T sine of 26.57 is equal to 20. Therefore, T is equal to 20 divided by sine of 26.57. And you must get the same answer, 44.71. So let's confirm. Another way out is that, you see, we are told that this is pulled by this force until equilibrium is obtained. Now, once equilibrium is obtained, then it means that this force here must be equal to this. So we can equate the T sine theta to also be 20. We can equally equate, once equilibrium is obtained, the weight is 40 Newton. Then we can also say that the T cos theta is also 40 Newton. So if T cos theta is 40, we can bring 40 here. What we have? We have this right angle triangle. This is the tension. This is theta. This side of it is 40. This side of it is 20. Knowing the adjacent and opposite, you can easily find theta. If you take, once this is adjacent opposite, tan of theta is equal to 20 divided by 40. And you can easily find the angle of tilt. Once you have the angle, you can use that to find the hypotenuse, which is the tension, easily. So that is another way out. Please, is that okay? All right. Let's switch to, so these are questions on the first law. Equilibrium state, either static or dynamic equilibrium. Now let's look at a question involving the second law. And I'll post this to you. Let's look at Let me take on the question. Okay, so I've checked on one of the questions. Please, have you seen it on the platform? Example 11. Are we there?
Please, which one?
No, I've just checked on the question, which I want us to look at. Example 11. A body of 5 kg is placed on a smooth plane that is inclined to the angle, to the horizontal at an angle 30 degrees. Calculate I, the reaction force perpendicular to the plane, II, the resultant force acting down the plane, and III, the acceleration of the block or of the body. Please, have you noticed it?
And please.
Okay, I want you to use 2 minutes to think through the question. Try solving it. 2 minutes. Right after 2 minutes, I'll come back to you so that we look at what and what we have to calculate for. So, a body of mass 5 kg is placed on a smooth plane. The smooth plane tells you that there is no friction. If there is friction, the statement to describe it will either be rough or you'll be given mu, the coefficient of friction. So once it's a smooth plane, it means there is no friction. So it's an inclined plane. Let's draw. And it is the angle of tilt to the horizontal is 30. A body of mass this is on an inclined plane. The mass is 5 kilograms. But the other things you must understand is that when a body on an inclined plane has its weight perpendicular to the ground, and this is the base of the inclined plane lies on the ground. So this is the ground. Its weight mg is perpendicular to it. So it makes an angle of 90 degrees to the ground. Now the reactional force, which is a force responsible for pressing the body onto the surface, is always perpendicular to the plane. OA, this is the plane. And the reactional force R is always perpendicular to it. When we extend this line, we have the angle between the weight vector and then the reaction vector being the same as the angle of tilt, 30. On an inclined plane, this component, the horizontal component of the weight, is always perpendicular to the plane, mg cos theta. This is always perpendicular to the inclined plane, makes an angle of 90. There is also a vertical component of this weight, mg sine theta, which is parallel to the plane. So mg sine theta is parallel to the plane. And if we check equilibrium, we realize that, okay, the reactional force is equal to mg cos theta. So on an inclined plane, the reactional force is always equal to mg cos theta. And this is the component which is perpendicular to the plane. The mg sin theta is unbalanced. There is no force balancing it. And I told you that this is the reason why when an object is placed on an inclined plane, it is always rolling down the plane, because this unbalanced force, this mg sin theta, is the resultant force. If it is balanced, then the net force acting on it is zero. But there is always a resultant or an unbalanced force acting down the plane. And so when you drop an object, it is always rolling down the plane. Please, class, are we okay?
Yes.
Class, okay, so calculate the reactional force perpendicular to the plane. Straight away, the reactional force is mg cos theta, which is perpendicular. This is always perpendicular to the plane. So the mass is 5, J is 10 times the cosine of the angle of tilt. And so we have 5 by 10 by root of 3 on 2. And this is 5, so we have 25 root of 3. Class, what is 25 root 3? What is 25 root 3?
43.30.
43.37 Newton. That is the reactional force.
This
How
is
many of
30.
43.37?
0.
Okay. How many of you got it? Okay. Priscilla. Who else? More hands. Hey, Charlie. I'm only having, who else? Lizzie. Lizzie also got it. Then Asumani, Ekuya. Okay. Okay. Adwa, thank you. Okay, then the next question. The resultant force acting down the plane. Once this is a smooth inclined plane, there is no other force apart from the always existing mg sin theta, whose direction is down the plane. And so that's the only resultant force. Okay, so the resultant force acting down the plane, resultant force down the plane is, so let's shorten it back, F subscript R, is the mg sin theta. 5 by 10 by sine of 30 degrees. And this is 5 by 10 by half. So we have 25 Newton as the resultant force acting down the plane. So simple. Right? Then the acceleration of the body.
Yes.
The acceleration of the body. Once there is a resultant force, then there will be acceleration. And the direction of the acceleration always follows the direction of the resultant force. So, Priscilla, what do you think will be the direction of the acceleration?
Down.
Priscilla, come again.
Mr. Lydia, please moving down.
Why will it move down? Why will it accelerate down the plane?
Mr. Lydia, I think it will move down because there's no friction. So like nothing is pulling it backward.
No, Priscilla, I won't buy your explanation. Why will it accelerate down the plane? Yes, somebody else. Why would the body accelerate down the plane and not up the plane?
Because it's on a smooth plane.
Lizzie, because it's a smooth plane.
Yes. So there's
Your answer is so smooth to be taken.
Okay.
I won't buy it. Why will it accelerate down the plane? More views.
Because that's the direction of the resultant force.
Come again.
Because that's the direction of the resultant force.
Exactly. I just said that whenever there is a resultant force, there will be acceleration. If the resultant force is 0, either the body would accelerate with a constant velocity or it will be stationary. But when there is a resultant force, if it's not 0, bodies would accelerate. Now the body accelerating always does so in the direction of the resultant force. The body accelerates in the direction of the resultant force. So while the resultant force is the mg sine theta, which is acting down the plane, then the acceleration would also follow the direction of the resultant force. Priscilla and Lizzie, are you okay?
Yes, please.
Okay, so pay attention. So Newton is saying that every acceleration is caused by a resultant force. So F resultant can be equal to ma. Therefore, if I'm looking for the acceleration, it is A is equal to F subscript R over M. What is the resultant force? 25. What is the mass? 5. Therefore, the acceleration is 5.0 meter per second squared. So beautiful. Somebody who is also a fan of formulas would go this way. Okay, the acceleration, the resultant force acting down the plane is mg sine theta. And Newton is saying that every force is equal to the mass times the acceleration A. So A is equal to mm will cancel g sine theta. If you are a fan of formula, then this is also another way up. So this is 10 times sine of 30. Since sine 30 is half, I have 10 times half, and the value is the same, 5 meter per second squared. I hope there's no question. Another follow-up question. Another follow-up question. And I forwarded that to the platform. A body of mass m kilogram m is placed on a smooth inclined plane of an angle of 42 degrees to the horizontal. The normal reaction perpendicular to the plane is 14.9 Newton. The normal reaction perpendicular to the plane is 14.9 Newton. Calculate A, the mass m of the plane. AII, the force parallel to the plane that is needed to hold the body at rest. And then the B part, if the parcel is pulled up the plane by a force 20 Newton parallel to the plane, find I, the resultant force along the plane. I, the acceleration with which the body moves. Take G to be equal to 10 meters per second squared. So make me proud. Make me proud. Let me see how you can put ideas together to solve this in about 4 minutes time. It's 1:56. Start work. Meaning at exactly 2 o'clock, I'm coming back to you. I'm going for commercial break. Hello. Hello.
Mr. Elia.
Yes, I'm back. So this time, there is an unknown mass. Our mass is unknown, M. We are to determine the value of M. Let me ask, Adwa, what did you get for M?
Please, I had 2 kilograms.
You had 2. Akuya and Amma, what did you get for M?
2 kg.
2 kg. Priscilla,
Yes, please.
what did you get for M?
2 kg, 2.0.
Okay. Then Lizzie and Inshira, what did you also get?
I also got 2 kg.
Okay. Okay. Then I think it's a unanimous answer. Eresi and Asumani, what did you also get? 2 kg.
I had 2 kg.
Okay. Now, once you all had the same answers, it means that we know reaction is equal to mg. I'm coming, let me turn the lights. Reaction is equal to mg cos theta. So once the question gave us the reaction, 14.9. So we have 14.9 equal to the unknown mass times 10 times the cosine of 42. And M is approximately equal to 2.00 kilogram. Now the next question. The force parallel to the plane that is needed to hold the body at rest. The force parallel to the plane that is needed to hold the body at rest. Chrysler, how did you do that? What did you get for that question and how did you do it?
Please come again. The next work was.
How did you answer the second question? The force parallel to the plane that is needed to hold the body at rest. What did you get and how did you solve it?
Mr. Please, I got 13.38. I equated it to like yes, please. I equated it to mg sine theta. Like You see, because the body is moving downwards, like I pointed it to the up, so I'll equate it.
Okay. And why did you equate it to the mg sine theta?
Please come again.
Why did you equate the force to mg sine theta?
Because like it's moving in an opposite direction, so opposite forces are equal.
Okay, let me pick Inshira's view too. Inshira, how did you answer this? First, what did you get and how did you answer the question?
I did mg sine theta
Why?
because they said the force parallel to the plane, and then the inclined plane, the force parallel to the inclined plane is the resultant force. That's why I did mg sine theta.
Calculate the force parallel to the plane that is needed to hold the body at rest. Akuya, what did you get and how did you also solve it?
Is it her? 13.38.
How did you solve it?
Since the natural force is mg sine theta, and for it to be at rest, there's supposed to be an opposite equal force. So you have to equate it to mg sine theta to get it.
Why must the force which will keep it at rest be equal but not greater? Why must the force which is supposed to keep the body at rest be equal to the natural mg sine theta but not greater?
Because it's supposed to keep the body at rest, and the body didn't accelerate, so it has to be equal to match it.
Okay. All right. So all the views shared, excellent. Let me quickly add something to what you've said so far. So this is a mass of 2.00 kg. On an inclined plane, the angle of tilt we are told is 42. There is always mg sine theta acting down the plane. So if you leave it, okay, if you leave it, please note that this force, this resultant force is parallel to the plane. OA is the length of the plane, and this is parallel to it. So if you leave it, it is always rolling down because as I said, there's a natural mg sine theta acting down the plane. Now we want another parallel force which will keep this body at rest. So it's like you want to stop it to stay stationary. Now, if I want to stop this from rolling down and then be still on the plane, will I apply a force, a downward force, or an upward force? Which of these two situations must be done? To stop this, will you apply a downward force or upward force? Yes. Inshira, will you apply, to stop this, will you apply a downward or upward force?
Please, upward force.
Upward force. Because when you apply a downward force, you are adding to the mg sine theta. So this is out. Now I want to stop it. Lizzie, will you apply a force greater than mg sine theta or a force equal to mg sine theta? You want to keep this okay, to be at rest or to be stationary. Inshira, will you apply a force equal to the downward force or greater? Hey, Lizzie, not Inshira. Lizzie, let me hear from you, Lizzie. Oh, her network is gone. Okay, Charlotte. Charlotte, will you apply an equal force as this one, or a force that is greater than this one?
If you experience an upward force,
I'm saying that will you apply an upward force which is equal to this or greater than this one to stop it? That's my question. Assuming the force applied is P, must P be equal to mg sine theta, or P must be greater than mg sine theta? Lizzie, I'm here. I'm listening.
P must be equal to mg. P
Why?
must be equal to mg sine theta.
Why not greater? Why shouldn't P be greater than mg sine theta?
It's
Lizzie, you will start with because. So because, and it is because. All right. Okay. So
because we want it to come to a rest.
the reason is that if P is greater than mg sine theta, the body will not stop. It will rather move up. It will accelerate up the plane. Okay, but we want to apply a force which will keep this at rest. So if we are keeping this at rest, then the force to apply in the opposite direction must be equal to the force acting down the plane. I just want you to understand the reason for our choices. Okay, so for the body to be stationary, then P in the upward direction must be equal to this. So it cannot be greater. All right. And so that's it. So P therefore is equal to 2 by 10 by sine of 42. And I'm sure that is what gave you 13.38 Newton. So this is the force which will keep the body at rest. Then there is another follow-up question. B. We are solving the B part. If the parcel, which is the mass, is pulled this time, listen, if the parcel is pulled up the plane, by a force 20 Newton parallel to the plane, find the resultant force along the plane. Now we all analyze this and then saw that for this to move up the plane, then the P must be greater than mg sine theta. Okay. And then you are given the force that is supposed to pull the parcel, which is the mass, up the plane, to be 20. So if P is 20 Newton, okay, 1, find the resultant force along the plane. Without spending much time, can somebody quickly tell me what the resultant force will be? Charlotte, are you there? So the force pulling this up the plane is 20 Newton. What will be the resultant force pulling the pass or the mass up the plane? Quick one. This shouldn't take you much time. Charlotte is gone. Yes, who is ready?
6.62.
How did you get it? Explain to us. Okay, explain to us how you got the answer.
for the body to move up the plane, the force applied must be greater than mg sine theta. So to find the net force, we subtract mg sine theta, which is a smaller force, from the force applied to get the net force.
Okay, but is the mg sine theta really less than the 20 Newton force pulling the parcel?
Yes, please. That's why it's
What?
able to move up the plane.
So, girls, this is it. For the body to move up the plane, then this force pulling it must be greater than the opposing force in the opposite direction. And the difference between the larger force and then the smaller force would give you the resultant force, which is pulling it. So the resultant force is equal to 20 Newton minus the mg sine theta acting down the plane, which is 13.38. And okay, what did you get? You said you had 6 point what?
6 Newton.
Priscilla and Co, Lizzie, Osmani and Co. Please, are you okay with the explanation?
Yes.
So when you understand these things, it is not difficult at all. Now look at the last question. Calculate the acceleration. Ensure your hand is up.
Sir, please, can you explain the resultant force one again?
You see, the question is saying that if the parcel, if a new information or a different one given, if the parcel is pulled up the plane by a force 20 Newton parallel to the plane. So we have this time around this parcel, which is the mass, is being pulled up the plane. But it is being pulled up the plane by which force? This force 20 Newton. Okay, before we made it stationary, by this time, this is being pulled up the plane by a force 20 Newton. Don't forget, the mg sine theta is always acting down the plane, the natural force acting there. Okay, so if this is being pulled up the plane by this force, calculate the resultant. So it's like a force pulling it and another opposing it. So the difference between them, okay, now for this to move up the plane, then it means the 20 Newton force must be greater than mg sine theta, which we calculated and had 13. So once the 20 Newton is greater than 13.38, then it will certainly move up the plane because bodies accelerate in the direction of the resultant force. So the resultant force certainly is the greater one minus the smaller one. And that's it. Are you okay?
Yes, please.
Now, calculate or find the acceleration with which the body moves. This body is now moving up the plane. Once it is moving up the plane, it means it is accelerating. And bodies always accelerate in the direction of the resultant force. So we have to calculate for the resultant force. Please do that for me in a minute's time, within a minute. Calculate the acceleration for me. I want to see how you go about it. Yes, your time is up. Oh. What have you had for the acceleration. Eresi, what did you get for the acceleration? Eresi. Hey, Eresi, are you there? Yeah. Erama. Erama, what did you get for the acceleration? Erama, I'm listening. Go ahead. Yeah. Erama's network. Okay, let me pick Asumani's view. Asumani, what did you get for the acceleration? Hey.
Mr.
Eresi, go ahead. Erama, rather.
Please, I had 3.31 meter per second squared.
Exactly. So the resultant force, which is responsible for the acceleration, is equal to mass times A. And what's the value of the resultant force? 6.62. Therefore, the mass is 2 times A. A is therefore equal to 6.62 divided by 2. We have 3.31 meter per second squared for our acceleration. So really not difficult at all. Not difficult. Not difficult. Okay, Amma, go ahead. Hello. Hey, Amma, reposition. Your line is breaking. Oh, rather unfortunate. I would hardly hear you. Hey, Amma.
Hello.
Yeah, I'm listening.
Okay. So please, for the AII, the force parallel to the plane that is needed to hold the body at rest. We got 13.38. So are you saying the 13.38 is equal to the resultant force for that question?
It's equal to
The resultant force.
You see, yes. No,
Okay.
listen. No, Amma, listen. We are looking for a force which will hold this mass at rest. This is the scenario. This is the scenario. A body placed on an inclined plane is always accelerating down the plane due to the unbalanced mg sine theta. So that is the resultant force acting down the plane. So it means that when you drop the mass on the plane and then you don't support it with some force in the opposite direction, it will always fall down or roll down the inclined plane naturally. Is that okay? Now,
yes,
if I want to hold this to be or keep this to be stationary, then I must support it with a force in the opposite direction. Okay, so if you are looking for a force which will keep this body at rest, then we must support it with some force in the opposite direction, and that's why we are only representing that by P. Now, for this to be stationary, then P must be equal to P acting up the plane must be equal to the mg sine theta acting down the plane. P is
Okay.
going here and this is going here. So for this to remain stationary, P must be equal to this. And so a
Okay.
force parallel which will hold this, keep it stationary, must be this. That's how come we establish that then P is equal to 2 by 10 by sine of 42. And as a result, we had 13.38 Newton.
Okay, so now the assumed force is 13.38.
Which
So
will,
they said if the
which will keep this at rest.
okay, but now that they've come to know that, hey, you guys are making noise. Now that they've come to know that, you guys stop. I don't like
we
it.
are having a very
Yes, sir.
bad feedback. They're singing around. The singer
Sir, please, can you hear
around.
me?
I can hear you, but there's singer tone at your background. I'm gonna go ahead.
Okay. Sir, please, can you hear me now?
Yes.
Okay. So now the question is saying that if the parcel is put up, if the parcel put up by the plane, if the parcel is put up by a force of 20 Newton, which is parallel to the plane, we should find the resultant force along the plane. So the resultant force is already 13.38. So does it mean that the 6.62 we got?
Don't call it.
Yes.
Now, see, now do not call it a resultant. Don't call mg sine theta a resultant force because now there is another force acting against it. Okay, so what you have to say is that yes, there is 13.38 Newton force acting down the plane. And now we are told that this is being pulled up the plane by 20 Newton force. And we are to find the resultant force now. Are you okay?
Yes.
This is natural, always existing. One, this is an inclined plane, but the mass is now being pulled up the plane by this force. So when it is now being pulled up the plane, find the resultant force now. Are you okay?
Okay.
So that is why.
So now the resultant force will be 6.62.
Exactly. 20 minus 13.38.
Okay. Okay, thank you.
Welcome. Okay. I think we have done much. We have done much. So when it comes to, unmute yourself. The singer tone must be over. When it comes to application of Newton's second law, it's about acceleration of a body, okay? And in the first law, it's about neutral and dynamic equilibrium, just that. Okay. Let's begin with moments. Sorry, momentum. We've done moments. Momentum. At least let's talk about this briefly. Let's talk about this briefly before next week. Can somebody share with me what momentum is? Your idea of what momentum is. What is momentum of a body? Yes, can any one of you share something with me? Amma, okay, go ahead, Amma.
The momentum of a body is the product of the mass and
Okay. Any more views? What is momentum? What is the momentum of a body? Any other view? Lizzie, Chrysler, Ishra, Eurama, Euresi, Asumani, Equia, Adjoa. Okay. When we talk about momentum, momentum can be said to be the amount of motion of a body, is the amount of motion of a body in a certain direction. Momentum is the quantity of motion of a body in a certain direction. So the quantity of motion of a body in a certain direction or in a given direction is what we term as momentum. The concept of momentum was investigated and researched by a German physicist, mathematician by name Gottfried, a German physicist, Gottfried Leibniz. Now, Gottfried was trying to quantify the amount of motion of a body. And this quantity of motion, he termed it as, the term he initially gave to the quantity of motion. This quantity of motion, he initially termed this as progress. So for him, when he talks about the quantity of motion, he termed it as progress, the progress of a body. Okay. For this reason, he represented momentum. Gottfried represented, represented momentum by the letter small p, small letter p. It is because of how he termed the quantity of motion as progress. So he represented it by the letter small letter p. So in physics and mathematics, momentum is represented by small letter p because he initially termed this quantity of motion as progress. That's the history behind momentum. Now, momentum is determined or quantified by the product of P is equal to the product of the mass of the body times the velocity. So momentum is equal to mass times velocity. So P is equal to mv. Momentum is a vector quantity, meaning that it has magnitude as well as direction. The momentum of a body always, the direction of momentum always takes the direction of velocity because mass is a scalar quantity. So if we have a given mass m with a velocity v in this direction, then the momentum of the body p takes the direction of the velocity. If we have a given mass m2 and its velocity is downwards, then the momentum of the body would follow the direction of the velocity. So wherever velocity acts, momentum also acts in the same direction. What it therefore means is that a stationary body has a zero momentum because momentum is a product of mass and then velocity of a body. So if a body is stationary, it has zero velocity, and so its momentum is zero. A stationary body has zero momentum. The reason is that it's because its velocity is zero. So the term momentum is associated with moving bodies, but not stationary bodies. No matter how heavy a body's mass can be, if it is stationary, it has zero momentum. Class, are you there?
Yes.
Are we? You are so quiet. Now, SI unit of momentum. SI units of momentum. Momentum P is mass times velocity. Mass, in terms of basic units, mass is measured in kilogram, velocity meter per second. And so the basic unit of, or SI unit of momentum is kilogram meter per second. There are other units. We have other units of momentum. You see, when we're going through Newton's laws of motion, we realize force, external force is directly proportional to change, the rate of change of momentum with respect to time. Newton's second law of motion. So F is equal to delta P over T. If we make delta P the subject, we have force times time. This is change in momentum. Delta P is change in momentum, whereas the product of the force and then the time taken for the exertion of the force on the body, we call this as impulse. So change in momentum is equal to impulse. Now, so delta P is equal to impulse is force times time, Newton times second. So we have change in momentum equal to Newton second. Because of that, or because of this fact, the other unit of momentum is Newton second. So either kilogram meter per second or Newton second is the SI units of momentum. Now the next I to understand is that yes, if two bodies have different momentum, what is it? What is that special thing about the bodies? Let me give you a scenario. If I have the same ball and I ask Priscilla to throw the ball to Akuya Adoma, okay, do it with all your might, Priscilla. When Priscilla throws the ball, then Mysteria, who is a macho man, whether you like it or not, okay, comes to throw the same ball, the same mass. The chances that Akuya will not be able to catch Mysteria's ball is higher than her ability to catch a ball thrown by a Chrysler. The reason is that once I am strong and so muscular, aka macho, I can give the ball a greater velocity than what Chrysler would give to the ball. The same mass, same ball. So me giving it a greater velocity means that the momentum of the ball in my case will be greater than what Chrysler can offer. I hope you are following me.
Yes.
Class. So if my throw goes with a greater momentum, the quantity of motion in my case, progress, is greater than what Chrysler would offer. And so if a ball is moving with a greater momentum, the tendency of the ball to continue to stay in motion is higher. The tendency of the ball, in my case, to continue to stay in motion is greater than Chrysler's. So if a body has a greater momentum, the tendency of the body to continue to stay or be in motion is higher. Okay. A body moving with a greater momentum would require a greater external force to stop it. Meaning that for Chrysler to stop my throw, she would have to produce magic, greater force to stop it than as for what Chrysler will do. I'll just stretch my hand and stop it. That is what it means. And so look at something, a charged elephant. Okay, a very annoying and then a charged elephant coming. Okay, the elephant has a greater mass, body mass, but the elephant cannot speed that much. But because momentum is equal to mass times velocity, even though the elephant velocity is small, but its mass is huge. And so nobody will tell you that, yeah, the momentum with which this elephant is coming with is huge. So run for your life. When you don't run and the elephant hits you or collides with you, the impact you feel is the momentum transferred onto your body. Please, are we fine? Another way, a bullet being fired. Nobody will stand in a path of a fired bullet. The reason is that the mass of the bullet, very, very small, sometimes 10 grams, very, very small. A bullet has a small mass. but it is designed in such a way that it moves with such a tremendous velocity. So if velocity is so much, if velocity is huge, however, its mass is less, the velocity, the momentum will still be great. And so once it is coming with that speed, nobody would advise you to run for your life. When it hits you, it is the momentum with which the bullet travels with, which will be transferred onto your body. And the fact that it has a pointed edge, and so the pressure associated with it is huge. This is the practicality of momentum. Any question?
No.
So we could deduce that momentum of a body is directly proportional to the mass. But this is on condition that at constant velocity, we can say that momentum is directly proportional to the mass. So for two different masses, the momentum of one is directly proportional to m1. The momentum of the second mass is directly proportional to the second mass on condition that velocity is kept constant. So if you have two masses and they are traveling with the same velocities, then you can say that the momentum of one is directly proportional to momentum of the mass of one and that of two. So if you take a ratio of P1 over P2, this is equal to M1 over M2. So you can be given a question where two masses traveling with same velocities. This is what you use to determine the ratio of their individual momenta. Okay, the momenta of the individual masses. We can also argue that for two different this is constant velocity. For two bodies, okay, with the same masses. So P is also directly proportional to V on condition that the mass at constant mass. So if you have two bodies with the same mass, then the momentum of the first one is directly proportional to the velocity of the first one. Then the momentum of the second one is also directly proportional to the velocity of the second one. This is on condition that the masses of the two bodies are the same, constant. So a ratio of this P1 over P2 is equal to V1 over V2. So two bodies of the same mass but traveling at different velocities have this kind of momenta. So the ratio of their momenta is equal to the ratio of their velocities. Please, any question? Please, any question? No question. All right, so if there is no question, then in fact, since we are starting a kind of new area, I'll end here. We have 8 minutes to end, but I'll end here because if we do much, it will be to the disadvantage of those who are not here today. But because you also made time to join us, that is why I felt well, it is their problem not to join us. So that's why we started. So this is where I'll draw the curtains on today's meeting. Please continue to enjoy the Christmas, but be very, very careful as you celebrate the Xmas. Okay, we'll continue with our lessons from next week. So take care of yourself and then bye-bye.
Bye.
All right, I'll upload the video. So